Howdy, hackers, and welcome to another episode of FairLight TV. So, recently there have been instances of people talking about cracking tapes on C64 in other YouTube channels. That's my home turf. So, in order for you to kind of deepen your knowledge about that, I would like to add a bit of extra to cracking tapes. So, we will go through the basics and we will also go through how to code a transfer routine where you can transfer the content of a C64 tape without actually kind of cracking the loader, because the transfer routine takes care of all of that without having to go through the loader manually. But that is reserved for people who watch the entire episode. So let's get started. Okay, so tapes, they are analog devices. And you don't need to understand the very technical details of how tapes actually store data in order to crack a tape. You just need to understand what the loader is doing at what part of the loader so that you can extract the data using the loader. What kind of black magic it uses to interface the tape, you really don't need to understand. But just briefly, to give you a bit of an understanding of how it works, let's just talk about that. So if you have a sine wave going like that, it passes like the zero. So if you think of the sine wave as like plus, and then it will go to zero again, and then it will go to minus, it goes like that. So the tape stores a zero. No, so you have two things. You have the amplitude, which is the height from the zero, and then you have the sort of the duration between when the wave passes zero and then to when it passes again. And this is used. This distance is used for determining zeros and one. So you have a short distance if it's a zero, and you have a longer duration if it's a one. That also means that the amplitude is a bit smaller for zeros and a bit bigger for the ones. So that is the black magic of how it works. Most of us would crack something that uses a fast loader, and the fast loader, it cannot like make the tape run any faster. So the only thing you can do is having the sine wave a bit shorter. So the zeros are even shorter and the ones are also even shorter. But you still need to maintain a security because tapes are inherently sort of a bad storage mechanism. You have wobbling and and a number of issues that can sort of happen to that bad quality of the tape. So if you are making them too short, it will simply not work in the tape environment because the tapes are sort of unreliable. So that is the technical implementation of a fast loader, making the zeros and one shorter. So if you listen to it using like a normal tape player, you could clearly hear the difference between like a standard stock kernel tape and if it's recorded using one of the fast loaders. So listen to an original tape. That might be a very strange pastime, but you can do that to sort of hear the difference between a kernel loader and a fast loader. Kernel is the sort of system area of the C64. It's between E1000 and up to the very end of the memory. And all the tape routines are there stored in kernel. Unless you have a Jiffy DOS, because one of the things that Jiffy DOS is doing, it needs additional storage, so it needs to sacrifice something, and what it sacrifices is the tape storage functionality. So that's ripped out, and all the additional Jiffy DOS stuff is stored there instead. So normally you trigger load from tape using shift run stop, and that issues a load. And then when load has concluded, it issues a run. So it stores load and run in the keyboard buffer. So you basically, it makes you type automatically, load, and then subsequently run. But you can also use the normal load command. Tape is device 1, and you don't need to determine that it is device 1. But if you want to load from disk, you need to tell if you want to load from device 8, which is the typical disk drive device for the C64. So, and what happens then is that the kernel routine starts scanning the tape if it can find a tape header. A tape header is sort of, let's say, like a database entry of what will be there on the tape afterwards. So it loads a little segment into a reserved area of the memory. It's from 033C up to 03F8. So that's the tape buffer. If a header is found, you would find that the first byte is the byte that tells if this is a plain file, which could be relocatable or not, or and then it could have 3, which is the non-relocatable file. That one works. That one always wants to load to where it's destined. If you look at any commercial games, they would be 3, so they would typically load to a very specific area of the memory for specific reasons that we will go through. And then you would have 2 bytes that tells in low byte, high byte order, that tells where the loaded file is going to start. So the start address, or where it wants to be loaded. And then there is an end address. To be honest, the end address it's not really important, because typically there is sort of an end marker on the tape. So you could typically kind of skip the end part, or that you cannot rely on the fact that the end marker is actually pointing to the very end of the routine you're loading. It could be a bogus value there. And then you have a number of bytes that tell the file name. And then from 0351 up until 03F8, there is basically empty space. They are not kind of defined as anything specific in the tape header. And for that particular reason, this is an area where fast loaders are typically imported. So the game starts by having the 5 bytes we discussed, and then the rest of the tape buffer is filled with routines that will be used in the subsequent loading of a fast loader. So it will load a little extra file that would eventually also use the areas from 0351 and upwards as part of the fast loader. For that reason, we're going into one of the specifics here, and that is autostart. So let's not do autostart. There will be autostart. Just give me a few seconds, because there are a few things we need to go through first. The entire process of cracking is sort of the idea that you would need to be in control of what is run, because you would need to regain control at a later point. So if you start the loader, you need to have made sort of patches or implemented mechanisms so that you would regain control at the later point in the process. And eventually, the ultimate goal is to set some sort of breakpoint or halt the process just before the program starts, because that is when you have everything in memory of the C64 and you can save everything out. And then the perfect version would also mean that you have the start address of the program, where the loader hands off to run the actual program. That is the ultimate goal. Ensure that you are in control of the process, so that and also finding that place where the loader hands off to the game. So if you just do load, shift and run stop, that means that you would load the program, and if it's auto starting, you don't have any way to kind of regain the control at a later point in the process. So we need to find mechanisms to regain control. And the classical one here is 63276. Okay, now he wants to press play on tape, and I need to do like that. And here we got the cursor back. So now I'm back in control. I called a place in the kernel memory. So using sys is addressing something that is in the C64 memory. And using that sys address, I called the specific address in the kernel that is fetching a header from tape. So what is the status of the machine now is that the header is read in. I can still manipulate it. And then I have another magical sys that will resume loading. And if I now first fiddle a little bit with what I have in the C64 memory, I can prevent the auto start from happening. And then I can manipulate when the file is loaded to kind of implement a new place where I regain control later in the process. So let's, and we will do this using the normal monitor here. So the, now I'm in turbo mode. So just briefly go through what we see here. O3 as the first byte on O333. See, that's the first byte of the header, and now this is indicating that this is a non-relocatable file. This wants to load to the place it's destined. And that address is O2A7, and the annotation here is as normal on the C64, high byte first and then low byte. Sorry, low byte, low byte, high byte. So this is going to be loaded to O2A7, and then the end address is, or could be, O304. The rest here is the file name until here. So O3, I actually think it's to here, right? So O350 is the last byte of the file name. So and if you see here, it's Velocipede. That was a randomly picked game from Assembly 64. One of the repositories you can access using Assembly 64 is one that contains disk images and tape images of originals. So this is sort of hacking an original tape, but it's in tap format here. Yeah, so 5645, that's VE, but the 05 here, that's a control character to tell that henceforward the printed characters would be white. And here the last one, it's 1F, and I would assume this one turns the cursor back to light blue, the same light blue here. So the file name includes control characters in this specific case, which is absolutely fine. You can do that if you want to have, you can clear the screen or move the cursor, but you don't have that many characters to implement that kind of movement. But it's quite... It's not unheard of that you would have a clear screen as the first character here in the file name. But from 0351, you would have the actual part of the actual loader. Yeah, so that's it. What you now want to do is you could change the O2A7 into loading at another place in memory, and it's good to keep the low byte consistent. So the sort of best practice here is to load it to 12A7, because then it will not trigger the auto start here. And I will just show you how the auto start works here as well. So when the file is loaded to O2A7 over to O304, it loads over vectors on O3. And the second one there, the one with what would that be? O302 and O303. That is the basic warm start. So whenever the load has concluded, the standard kernel process will jump via that vector, which is now updated to point to the beginning of the loader. It points to O2A7. So this is how this particular auto start works, and it's a quite common mechanism. It's quite easy and it's quite convenient. So a number of loaders use this very trigger for triggering the auto start. Yeah, so yeah, let's do that. And now if you want to resume the loading, you would do like this. But we would do one thing first, on, and then fill 1000 to 2000 with zeros. Okay. And now we exit the monitor again. I'll go through the cleansing process, why that is a relevant thing. And now we speed things up again, and now we're done. Okay, we go back to the monitor, and then we do 1 to A7 because that's where it's loaded now. And here you see that this is the actual start of the loader. So this sets up all the basic structure. It's and then it's looping here in the compare FA. It's looping and looping and looping. And when FA changes, and that is when the loader is done, that's how it's signaled. The actual loader interrupt is signaling that it's loaded the entire file. And when that file is loaded, the loader jumps to 8000. And I'll show you the game in a few seconds, so you will see that. But so that is sort of the first start address. But the real start address for the game is actually also there, because this 8000 and the first file it's loading something to 8000, which is sort of an in-game, a loader game. So you can play a little game while you are waiting for the game to load. But that is only until you've loaded all of the game. So 03, and yeah, the rest of the loader is still here. So the actual start address is here, C600. It's very, very easy. This is a very old game, so having like the start address in clear text like this, it's not very common. So there are like 3 ways which we now can ensure that we regain control when the game gets to this point, depending on sort of the cartridge we're using or the facilities we're using. So if we're using Action Replay, we can go into freezer mode and issue an SF here for set freeze. That would exchange this jump to jump subroutine to DFD3, which is part of the IO area, which is the interface for the cartridge. And when that is triggered, Action Replay then replaces the jump C600. So set freeze is setting its temporary, it's making a temporary change to the code you're wanting to exchange here. But this does only work in freezer mode. It doesn't work here in the normal monitor. So if I do this now, it would not work. I need to go into the freezer before I do it. All right, so that is one thing. But if I have an expert cartridge, they don't have that functionality at all. So there you and also in Super Snapshot, that's typically the same. And then you need to replace the jump here to something which is stopping process, where you then can sort of enter the monitor and you know that you are on that particular point. And yeah, a qued of triangle used to do set carry and then branch on carry set. So it's setting one of the flags in the flag register, and then it's branching, and it's an eternal loop. You could also exchange it to a jump to itself. That would do the same thing. So here you could do jump to 03 F4. That would also just loop, eternal loop, and then you can just enter the monitor using a restore key. here I'm running Vice, so I have the opportunity here of using breakpoints. So I can just do break C600. Let's see if I can. No, I can't change these. So here I just added a break to C600. And that will stop everything just before the game starts. And then I have a clean start address. So these are the three ways. So action replay, set freeze, super snapshot, and the export cartridge. To make some sort of eternal loop so that it stops, and then you slam your restore to actually evoke the machine code monitor. Or if you are running Vice, you don't need to interfere with the C64 memory. You just need to traverse the loader and establish that you know where it's going, and then you can set a breakpoint in the emulated environment, which is totally invisible to the program. So I can do it in the old-fashioned way, but there is absolutely no benefit of doing it the old-fashioned way if I'm doing this in Vice in the first place. It's so much easier to just set a breakpoint in the Vice emulated environment. Okay, so episode 14 and 16, they are about cracking tape. So if you would like to have like another explanation, because I'm not explaining this using the same words, do have a look at episode 14 or 16 if they might give you like additional feedback that might be beneficial for you. Unless you just ask a question, and just ask a question in the comment field below, and that's absolutely fine, and I will try to answer most of them. Episode 22 is also about the crack project. That might also be beneficial as a reference for you. So have a look at that one as well, and you would see how I do things when I do like the post processing of when I've extracted the data from the actual tape. But talking more about the mechanisms you are likely to find, because very, very few of the projects you would dive into would be as easy as this one. So when you look at the jump routine, the jump address here in clear text, you never see that anymore. It doesn't work like that. There is an RTS or an RTI, or it uses some other mechanism not to print the jump address in clear text. So first, the first mechanism of protection is of course the auto start, because that means that you couldn't get back control. If your game was just stored using Commodore stock loader, you could just do load, and then you enter some other device, and then you do save. That would work, because you would be getting back control after loading concluded, unless you press Shift Run Stop. But if you just type load, it would load, and then you would have control, and then you would do save, and then you would have a digital copy on the new device. But again, so the first sort of level of protection is the auto start. What a number of programs are doing is that they are overloading, which means that as part of the data it loads, there are segments that loads over the loader itself. It could mean that it loads over the routine with the same content. So if you applied any sort of patch, that would be gone, because the data would then sort of eradicate your patch. It would load over the area you patched, and your patch would be gone, and you wouldn't have any control anymore, because it would use overloading. But what you can also do is having like the routine working in some ways, and then you load something else than was there originally, so you could change the behavior of the loader by adding new loading into a new segment into the loader. That's also, rather common, I would say. And then you also have decrypting and trashing. So if you look at Cyberload, which is part of what I've been recording before, the area it loads first, the area that sits in the tape buffer, that is encrypted, so there is no visibility of what's there. It's the tape buffer looks like it's full of junk, And then you have something loaded to O2A7, as we saw in the example here before. And the first thing that one is doing is decrypting the stuff on O351. And then it's calling it when it's in decrypted form. And Cyberload is one of the better loaders on the C64 because it uses a number of those tricks. The overloading, it's of course auto-starting, and it's also overloading. So any patches would be gone. But what it's also using is that it's not actually one loader. There is a first loader that loads a more complex loader, and then that loader has it's faster and it uses a number of other features. So there are, and then you have a level loader as well. So Cyberload is not, it's sort of a portfolio of options. It's just not just one, like in the example here. Yeah, that was discussing the protections of tapes. I mean, deliberate errors and hiding stuff in the media which isn't visible via the normal file system, as you can do with disk. These are not functions that exist in the tape environment because there is no like data that is not visible to the operating system, because we're out of the scope of the operating system anyways. All the fast loaders are using stock kernel routines to load the first part, and then they take over, and then you can rip out the kernel, and the kernel is not needed anymore because it's using its own fast loader instead. The kernel is not in use. And deliberate errors, unheard of in the tape environment. Why would you want that? Tapes break anyway, so you don't need to break them deliberately. Yeah, that was a brief thing on protection on tapes. So if I want to make a cracked version of Velocipede, I now have two options. Either I set my breakpoint to this jump to C600 and then just save out the entire memory there. Or I try to extract the segments as they're loaded from the tape. And why is that different? Well, first of all, when I make my version, I would like it to be as clean as possible. There shouldn't be any junk in it. And the reason for that is that I would like my version to have a small disk footprint. It's sort of a merit of a C64 crack that it is as small as possible. And then I would like to ensure that there is no areas of memory that I'm saving that haven't been initialized before. So if you look at freezed versions, they are basically taking a snapshot of the entire C64 memory, areas not relevant to the game at all. And if those areas haven't been cleaned before, the compression that is applied is less effective. So if you look at the freezer cartridges, they typically have one of those like initialize memory first. That is storing the entire memory with a byte. For action replay, it should be BD. Typically, the hacked version would install a 0 instead, because that typically packs even better. There is typically like special handling of zero field memory to make the compression more effective on those things. So compression is applied to ensure that the footprint on the disk is as small as possible. But in order for compression to work, we need to ensure that it only packs valid data and not crap that we don't want there in the first place. Yeah, so think of it like if you are really good at packing your bags when you're traveling, even if you are the absolute best bag compressor in the world, the fewer things you bring with you, the smaller bag you can have and still maintain all of what you need there. If you have like one bag of stuff that you're going to need, and then you add 50% more of stuff that you just bring, but you're not going to use in the final location, you will need a bigger bag, even if you're super good at compressing everything into one bag. It's sort of that, ensuring that you isolate the data that is the actual game, remove everything else, and then it packs nicely to a small disk footprint. And that's what we want. A program that starts when the loader hands over to the main game and only contains the stuff relevant for the game so that the disk footprint is as small as possible. That is how you crack a game. You do not freeze it, and you do not retain crap in memory that is not needed for the actual game. That is the skill of a good cracker. Let's just have a look at the game because it's sort of cute. And then we play. Okay, now it's loading something to 8000. It's the Micro Painter, which is a program, which is like a loader program. Many people would have heard of Invader Load, which is sort of a Space Invader game. But this is something which is, I think it's more like Sticks, not really sure. So a special game that you can use in the pastime for before loading the actual game. Yeah, we're not going to play the game. I'm just showing you that this is also in the memory at 8000 throughout the loading process. We can do break C6. So I'm adding that break now. And it's fast loading. You can see the counter on the top right. It's counting down. Right. So now the program is loaded, and now it's going to jump into the address C600. So if I save everything now, the entire memory out, I would also get this Micro Painter program. So Micro Painter is in the memory. So unless I fill that area out, Micro Painter would be part of my initial release, even if it's never run inside the actual Velocipede game. So if I want to make the smallest version, I would like to ensure that that portion is not there. So if I save it now, and if I pack the program and set my program to have C600 as start address, I would have a very neat version, but it's not as small as it could be. You will see that it starts immediately here. All right, so just to show you how the game works. So in the episodes where I discussed tape cracking before, I show you TapX. So during the first few years of my cracking lives, I was cracking everything manually. I cracked all the loaders, and I made annotations, and I had binders with sort of quick references. So when I was cracking a loader again, I could just look at my old notes, and I knew how to sort of defeat it. When I was more involved and I had more contacts, I got copies of people's transfer routine. I wasn't even aware of the concept transfer routine. So these are programs that extract data from the tape, save it to disk, so you wouldn't have to bother about the actual kind of cracking of them. Nowadays, I'm having this great option where I can just take a tap file, and we are now taking Velocipede here. And then TapX is doing its work on that. It's analyzing that because it knows like all the loaders, basically all the loaders. So here you would see the content of the game. Let's do file details here. So here 033B to 03FB. Okay. So as always, Commodore stores the header twice. and then it stores the data also twice. That should also possibly be mentioned when mentioning the fast loaders, because fast loaders always load the game just once. They don't have 2 copies of it. They just have 1 copy, which means that it's halving the loading time in the first instance here. And you see here the O2A7 loading to O303 or O304 as it's stated in the loader. That's what we saw previously when we hacked into the loader. And then the first file that the actual loader here is loading is from A1000 to BFFF. So that is the Micro Painter game. It's calling that when it's done. And then when Micro Painter is running, in the background, it keeps loading. And the next thing that it loads is from C1000 to C8FF or C900. And then it's making a big load here of 0800 to 8FFF or 9000. So this is what we know that the game would eventually consist of. So if I would now like to make a version of the game, and I have applied that breakpoint at C600, I can now fill out the area between A1000 and C1000 because I know that is sort of the Micro Painter game. That's not going to be needed. All I need is this from C1000 to C900, and then it's from 800 to basically 9000. The rest could be filled. So this could load from 0800 up until C8 or C900, clearing the area under the basic ROM. Tapex would tell me this, but one other way would be if I was able to extract the data such as this, rather than just loading everything into memory and then cleaning memory afterwards. If I just ensure that I make a version that only consists of these 2 files, that would be the same, because then I wouldn't have any redundant data that would be artifacts of something else that was there to start with. So let's have a look at my transfer routine now. So I coded a transfer routine for this, and that transfer routine, the source code for that, would be in the GitLab repository for FairLight TV. So if you don't have access to that, let me know and I will grant you access to that. In exchange, you could share the link to this to ensure that everybody else would have access to it. If you do me a favor, I'll do you a favor of sharing you that access. So let's go over to the actual transfer routine then. Okay, so tape transfer, a program that extracts data from the tape to disk so that you don't have to manually crack the loader. You just have the data from the tape into the disk, and then you can start manipulating and making your version from that. I have attached now a disk image to my emulator here, which contains my program, and then the rest of the disk is full, so empty. So there is plenty of space to store the extracted data. And then I've also attached the tap file here. So okay, so press play. I'll do it like that. Now we can have that. And now it finds Velocipede. You saw that the file name was sort of strange, so part of the routine is, as I'm clearing control codes here, so it will just find the actual file name rather than those weird data things. And it also extracted the start address for C611, which you already know it is. And then it would start loading from the tape, and it's found this portion of 8000 and save that to a file name called 0.velocipede. Yeah, and now it's saving the second one here. And this is the long one. It's from 800 to 9000 basically. And that's when it's done. So let's see here if we, and of course, so I present this at the top and this at the bottom. There is nothing presented, so why don't I just print something fancy in the middle of the screen? Yeah, because this is where the code is. So if you take a look in the machine code monitor, you would see that the actual tape routines and all my utility code is here in the screen memory. Everything is here. So basically the entire memory from 0800 up until the end of the memory is available because the code is here. And I will show you the source code, but that's how it works. So there was no memory left for doing anything fancy. I could have said that transfer complete or whatever. Yeah, let's just reset the machine here and let's see what we have on the disk. So we have is it joysticks enabled again? That crap. So 0. It's loading from 8000. 1. C1000 to C8FF. Let's yes. So here you have it. That was the start of the program. And then we can do load 2. Big program. That's actually a piece of BASIC. So Carl Hörnell, who has done Velocipede, he coded parts of the game in BASIC and parts of the game in machine code. So yeah, all the poking here is sort of annoyingly much. But let's clear the memory here, and I will just show you how. So 1, like that. 1. And then 2. So now I didn't load the 0, the micro painter part. And I can do like that. Oh. I messed up. I had to load that again. Now we've identified the 2 files that we need. They are the 1 and the 2, and we should call that using C600. There is a bit of an issue. I think that now I need to turn the joystick back on again. Possibly also turn the volume down a bit. Oh no. Oh, it works. It was fine. Okay, so here you have it. That's the game. Just to show you the process here, I use 6502 bench as I normally do. Andy McFadden, I've said that you are making a fantastic program, and even if I continue to nag you about suggestions, I still use your program and I still like it a lot. So this is it. So I just reassemble it. And if you remember what it looked like when we saw it directly in the C64 memory, this is sort of the same. The stuff I need to do here is set the IRQ vector, because that is something that is rather special. The 6502 bench does not pick that up automatically, but so I have to do that manually. What else? Yeah, there is this little thing. So it takes a value and stores to 0366, and 0366 is here. And you see here that, so the interrupt is triggered pointing to here, and then it sort of makes a branch here to some place. And depending on the value of 65, 0367, that branch will go to different places. So this is sort of the self-modifying, a bit tricky code to follow, but here it stores OD. Default here is that it branches to here, store O2, but then it changes that to OD, and that means that it's going to branch to this place, and eventually here it stores O2 back to that place again, but if it takes other routes, it could store 29, which means that it's going this place, or it's storing 40, which is going here, or it's storing 52, which is going to jump to here, or 71, which is going to be here. So if I insert any piece of code here in my reassembly, then I need to change those values. Otherwise, the branches wouldn't go to the right place. That's sort of, the pros and cons of self-modifying code. I would need to recalculate those values if I would like the opportunity to insert stuff there. But I didn't really need that. I didn't need that. So what I've done in the final program, I use basically the reassembly as it looks here. I've inserted stuff, but it takes the same number of bytes. So I've ensured that I don't sort of change the number of bytes, because then it would be very difficult. All right, so this is this. So, and then I do assemble, and I use Turbo Assembler, and then I generate the source code. So here it actually generates the source code. I now take this, the entire source here, and then I use this. This is the noise TASM to kick assembler converter. I just paste in my code here. So I just did a copy V or control V to insert the stuff that I just copied. And then this one generates the kick assembler code. It's not perfect. There are sort of issues with the kick assembler code, but it saves a lot of manual labor for setting the what? Okay. Yeah, well, whatever. So the kick assembler code here should work now, but it looks like the labels doesn't have the ending colons. Yeah, whatever. It worked when I used it the last time, so I'm fine. I'm absolutely fine. So I would generally recommend that way of working, that you generate an assembler, use assembly here with 6502 bench using the turbo assembler annotation, and then you use the noise converter to convert that to kick assembler, or if you would like to use turbo assembler, that's absolutely fine. It's just not what I use. So yeah, now let's move to the actual source of the program you previously saw in action. I did 25 minutes of recording of showing the source, and after that I found a few things in my source code that I didn't like. So yeah, let's record another one after I've updated that. This means that the source you see here is not producing exactly the output you have seen in the previous part where I do the transfer. So I mean, they are minor things and might only be important to me, but if you are really attentive to the details, you might see a few of the changes, like the 3 lines in the beginning. That's sort of the main thing that's visually changed. Okay, so this is the tape transfer for a loader type Tapex calls microload. I have actually not found another one that can transfer this exact loader type. And to be honest, I don't have any statistics of how frequent this is. So this might be the only game that features this loader. What do I know? But at least this one works for Velocipede. I'm absolutely positive it does. It might also be that I fiddle a bit more with it. So when you have access to the GitLab repository, it might look a bit different than this, but I mean, the gist of it should be the same. So that said, there are a few things that really needs to be said. And the first one is that Fungus of Nostalgia released a number of transfer routines, source codes for them. To be honest, I don't think I have any like binary, so I can't really run them. But and the ones that he released are also not really functionally complete. There is supposed to be like lines that are copied to the screen, which is the instructions, and that is sort of in a separate file. That's not in the actual source file, so we don't know what they would be. But at least there are key parts of his code that I've used here. I just plainly copied. Some I've copied and adjusted. Some I just plainly copied. Because I haven't done any transfer routine on the PC before. I only have that in my own turbo assembler environment where I did my own Cyberbuster, which is the routine that copies Cyberload. So I was glad to have Fungus's work to just kind of digest, because then I didn't need to rewrite it or reinvent the wheel. So humble thanks to Fungus. You are seriously competent. I've said it to you, and I'm happy to say it in public as well. So great work, and thanks so much for this. You didn't give any okay for me to use it, but I'm sort of using it, assuming that if you are releasing it in the public domain and I give you proper credits, that shouldn't be a problem. I should also say that I'm heavily inspired by the guys on Agile. They used, or they provided the transfer routines that I used mostly. Especially Synchros Cyber Transfer version 2 was really good. K12 did a lot of things, but they were more specific to one game or a few games. So and just testing through them was not really what I did. So, but he released a number of these transfer routines, and all of them were really good and worked absolutely flawless when I tested them. Okay, so now we will run through the source code, not in super detail, but detailed enough for you to sort of get what this is doing. And again, if you have access to the GitLab, just let me know if you want to get access to that, and you can download the source and you can build this yourself. I will include everything you need, so you could just build it with KickAssembler and you would have a working output. So from the screen, yeah, I possibly should do like this, so you just see how it looks. So I haven't associated any tape with it. So, okay, so the heading is now 3 lines, and you have the command line here. It should also be centered. And now I press play on tape, and then it does all the rest automatically. The rest looks like it did in the demo before. So we're quitting that. I'm calculating the place where the start address is placed in the first original message when it tells where it's found stuff. And this is the address where it fetches that address from the from the memory. So that is where C600 was fetched. That's where it placed on 03F5. Okay, and then I use a few variables down at the 0 page. So 2, 3, 4, 5, 6 for temporary storage. I'm generating a basic header here. I know that there is this basic upstart thing in KickAssembler. I prefer to do it like this because I can then give the line number the very value I want. So I don't have any control over it if I allow KickAssembler to use its own work. Basic end points to the next basic line, and that needs to be 3 zeros, and then basic is terminated, and there is no more basic, and basic knows that, so that's that. That's this one. So the line number, I give that in decimal here. Kickassembler wouldn't mind that I give it in decimal, because when I do the list, this is going to show up in decimal. So why not print it here in the source the way it's going to appear in the final product. 9E that's a plain sys, so the tokenized basic token for sys is 9E. And then I need a string which points to the start address. Thing is, you would possibly want something like this, to int string start and then just post it here. Thing is that does not work, because that can only be used after start is defined. So I can't use it up here when start is down here. So what I'm doing here is I'm printing the calculation of what start should be, so I can compare it in the output. So I just build it another time, and I see if they are okay if I change it. But I mean, it only happens first time, and then I don't change it, and then it's correct if it's correct the first time. Okay, the first portion here would be a lot of this is the stuff that Fungus is doing his init. So storing the current drive. So if you are loading the program from device 9, you are assumed to also want to store the data to device 9. So it's restoring this. So it's not one of those programs that is really stupid and saves to device 8, regardless of if you loaded the program from device 10 or whatever. Okay, turn off the screen, disable NMIs, so basically pointing to an RTI, I think. No character shifts, yes, that. And DO18 to 17, that's the default value. It sets the font to default value, and it sets the screen to 0400, so which is presumably already, but yeah, just doing it. We don't want any kernel messages, so we turn them off. Colors, all registers set to 0. So there is a slight difference between kernel version 0 and kernel version 3. So if you do a clear screen, one of them takes the value from DO21 and one takes them from 0286. I don't remember which one is which, but if you do it like 0 and then just clear the screen afterwards, it would be the same regardless of kernel version. So this is also taking care of potential differences between kernel versions. Okay, the tape motor is controlled via the 1 bit in address 01. Setting 2F properly so that it's all input, I think. Yeah. And then we can poke the proper value into 01 so that motor is off. That's sort of the default. So now we have the opportunity of turning motor on and off via 01. And that is absolutely something we would like to do. If you press and motor is running, it would keep running. Even if you're not reading anything from the tape, it keeps running. So if we load a segment and then we save it to disk, unless we stop the motor from running, you would be on another part of the tape when the loader starts running again, because you let it run while you were saving to disk. So the proper modus operandi here is load from tape, turn motor off, save to disk, turn motor on. There you go. That's the way to do it. Okay, clear screen, and as I said, the having black in the background was important here. Print the main message, so that will be the 3 lines on the top that tells that this is a micro load transfer made for FairLight TV. And then put screen back on, and then populate loader. It doesn't really matter. We could switch switch these two around, but populate loader is copying the loader code from where it resides in normal when it's loaded down to the screen memory. And then it prints the press play message. And the way I've done it is I have a set of messages, and I have a general routine that prints hex 28, so one line of message. And then I have because I have a number of messages, I'm selecting which of the messages by Y. So messages is the start label, and then message press play is one label. So if I take the latter and just subtract the start, I get the offset to that one. So this is calculating the offset to the particular message I would like for this particular instance. Okay, and then detecting if you pressed play on the tape recorder, I could do it like this. So I load 0, 1, and I'm assuming now that tape play isn't already pressed, because if it is, then we get into trouble here. So, but if it's not, and then you press play, there will be a change in 0, 1, because it will signal that the motor is sorry, the play is now pressed, and then it will continue. And then CLI is starting the interrupt, and then load head. It's a routine that loads the header, the one from 033C and onwards, the one that contains the values of the start and the end, and well, that second part of the tape loader into the tape buffer. And then when that is happily passed, we print a message that we found a file, and we tell which file it is by copying the found file name. And I've done a rather special thing here, because Velocipede contain those two control characters, and I really don't want control characters. If I export them as file name, because this is also used as file name when I save the file, it gets a bit weird. So basically any character under hex 30 should not be there, because they are control characters. The only exception is space, which is 20. I could potentially also have removed anything above, I don't know, 60 or something, but if I don't want upper and lower case. But this is just ensuring that I'm capturing the actual issue with Velocipede, giving the control characters, and they are all, both two of them are below 30. Okay, so I'm only, if I find one of the control characters, it's not copied to the file name here. Reading keeps going, but the storage is not incremented if we find one of those. Okay, so we print to the status box, there, and then I also have a copy here, which is the file name I'm then going to use for the save. It starts with 0 dot and then the file name, which means that I need to calculate where I should poke it into that string. And then I also do white background for this. So status box plus D400, that means that it's D800, because the status box is on the screen memory starting at 0400. All right. Yes, and then I'm picking the start address, and the start address is found on 03F5. That's where the address of the jump that starts the game. Yeah, where were we? Oh, here. So that's that, and then I have a general print address, which prints, and also here the Y tells where in the status box that is going to end up. So I have the status box already on the screen, and then I'm printing the four numbers that is the hex of the start address. So this one will print the C600. Okay, and then I have my key wait routine that waits for a key press and flashes the border a bit to tell it that it wants some sort of input. And then it's doing jump to tape start, and tape start here starts the general tape loader. And as I've noted here that everything is now copied onto the screen, and all parameters are fetched from the loader itself. And that means that once I am here, I can load freely up from 0800 upwards. There is nothing in the memory that I need to retain now, so everything could be seen as sort of empty memory. Normally in a transfer, you might also always load to 0800 because that gives you the biggest freedom. As long as you sort of retain the save addresses, where you actually store the program or where you load it into memory doesn't really matter, as long as you know where you're saving it, so it appears on the disk on the proper location. Here I haven't done that. I'm actually loading to the very same location that the game loads. It's a matter of taste. Again, it works for this game. It might not work for every game. So especially if you have data that's under D1000, then at least you need to do bank toggling, and I'm not doing any bank toggling here. Okay, and now the support routines, and these are only the support routines that are there until we do the tape start. So I cannot use these routines afterwards because they are in plain basic memory. So loading the header, tape on, setting up, set logical file and set file name. And for tape, we don't need file name here. It's basically load any file. And then get the header and load the header. And then turn tape motor off. So this, that's a totally redundant RTS. We don't need that because we do jump tape off. And that jump also includes an RTS, so the subroutine is ending when we jump to the tape off routine. Shaved off a byte, yes. Every byte saved is a byte saved. Okay, populate loader is a simple routine that just copies the loader from where it is in memory when it's loaded to the place it's supposed to sit on the screen. And the way it's written is that when it appears on the screen, all the jumps are correct because it's written like it would sit on the very location it's copied to already. So I'll show you that. Oh yeah, already now actually. So loader is the source where it sits, let's say 0900 or wherever it is now. Sudo PC says that, okay, well, assemble this piece of code as if it was placed on 0478. So any reference to any address inside the scope of this sudo PC, the curly brackets, will be as if it was coded on 0478, which is where it's copied. So when it's going to be run, it is going to be on 0478. It's just not there yet. So tape IO sets up the IO for tape, logical from the name. And then it prints the message that I'm now searching and loading for anything on the disk, on the tape. Turn on tape and then await FA. So the 0-page address FA is what the loader uses as the flag to mark if it has concluded loading a file. It starts with 3. When a file is loaded, it decreases, so it will be 2. So I think this is sort of a static thing in this loader, that it's supposed to load 3 files. So when FA turns to 0, all the files are loaded and it should not continue loading any more files. But that counter could also be used as sort of a trigger to wait for when the loader has concluded loading. I made that into subroutine. That's part of the loader, but I extracted it out. So, and then there is a bit of an issue with the last file, so because that exits a bit differently than the first 2 files. So I needed to make this. So final save is well, capturing another location in the loader, calling here to ensure that I save the last file as well. Otherwise, it will just sit there and wait. So tape off means that I'm now shutting the tape motor off. I am calling the save routine to ensure that so tape motor should be off when the loaded file is saved to disk. And when saving is done, I am checking FA if this was the last file. If it's not, you could jump up to next file and it will continue setting up again, printing that it's now loading another file. And turning on tape and waiting for the load to conclude. So this starts the load, this sort of ends the load. And this is the really ugly end. There could be sort of an error or a message saying that I've now loaded all the files, but it doesn't. It's just flashing the border in a different manner than the one where when you're supposed to press space. So the FA, it's hard coded as 3 in this program. So if this loader is used on another game where there are more files than the 3 to load, then this is hard coded. I'm not picking this somewhere from the loader, which might be an issue that this is not fully generalized. It might only work for Velocipede or other games that consist of 3 loadable files. Okay, waiting for FA looks like this. So clear interrupt and then load FA and then compare and making an eternal loop until FA has changed, which it will when it has concluded loading a file. Okay, so again, more subroutines. This is an init. This is the init. The key thing it's doing, it's setting the IRQ and also, of course, the timer here. And then switching out all the ROM bank. So it's only the IO bank that is turned in. Kernel is no longer needed. Basic hasn't been needed at all during the entire process. But we don't need any kernel routines because we have taken over. There is no standard tape routines needed anymore. And then it's doing a bit of a delay here before it returns. Okay, and then the IRQ is set here, and the IRQ is triggered and points to this direction. It's always good to have some sort of sign that there is activity. It's doing dec dbe9. To be honest, that's just one address of color memory. I don't know. I can't see that does anything during the load because that address is not really visible. It's not. There is no content of it. Possibly during this micro paint, it might show something on the micro paint. Yeah, well, whatever. We don't need it because micro paint is not going to be part of this loader anyway when we transfer it. So that one can go, and in order to have some sort of activity that something is happening, we can do this. I'm taking AB, which is like a CRC that the loader is generating to ensure that you have full integrity of the data. When it has loaded, AB should have the correct value. If it does not, there is a load error and then it would fail and it would reset. But I'm taking this value and poking it to the color register. So there will be some sort of flash, and it will be a bit different depending on where you are in the loader. It's always nice with flashing borders. Okay, and the key part here is 0366. So what you see here is a branch to 02. So it's a branch, and then the next instruction here is 02, and 02 means that you should flip 2 instructions forward. So this would be 0, this would be 1, and this would be 2. So branch on equal and then followed by 2 would end up here. But if you see here, what it will do next is that it would store OD. So this is how it controls. It's self-modifying code that changes that branch to different parts of the loader depending on where it is. If it's found the file it's looking for, then it's going to change into one place. If it has loaded all the files and it should conclude loading, then it would store another thing here. So you would see that it stores to 0366 plus 1, which is again the sort of the distance the branch will take its branch. Here it's back to, okay, start loading again. Start finding a file here. Here it's 29, and then I've given the label here 29, so store 29. I mean, in an ideal world, you would calculate this value given like a difference between this address and the label you were branching to, and I'm sure that was how it was in the original. I didn't take the time to do that. Yeah, that's the proper way of doing it. As long as I don't insert anything, this one works as well. So we're doing it like this. Yeah, and here is a bit of a thing where I injected something. So store vectors, when this happens, it has loaded the values of FC, FD, FE, and FF from tape. And when that is done, it goes into a new mode where it starts loading using those parameters. And I'm going to try to explain what these 4 values are. FC and FD, they are very logical. That is the start address of loading. So as soon as you have loaded all of them, it will go into this where it starts saving to that address. What FE and FF is more difficult to explain. The number of bytes that is supposed to be loaded is not that. It's the delta between that and FF. So think of it like a starting value of a counter. It would always count to FF, but the starting address is loaded here. So if it's going to load hex 1000 byte, the start address would be F000 or F1000, because then it would load the hex 1000 bytes. So the start of the counter, and so the delta between FF and the value given here tells how many bytes the loader is going to load. Normally you would have like the end address, or you would have a counter that counts down, so it would give you the number of bytes. But this is sort of, no, it gives you a value, which is the starting counter of the value, which will eventually go up until FF. A weird way of doing it. Okay, yeah, I don't think I need to explain anything. Here is if loading failed, where the AB is wrong, then the program will just reset. I haven't done anything else. It's possible to capture that and tell there is a load error, but I don't have that much memory left for additional error messages, so I'm skipping that. So this is what you get. It will do a reset. There is yeah, that's what happens. And the way it was in the original, this is the routine that detects if it was the last file that was loaded. I tried to simplify this, but yeah, it became more complex. So the simple thing was just to keep this and add a final save, and the final save jumps to this specific routine, the specific part of my main routine here, which does the save and then is done, because then FA is down to 0. Okay, store vectors. Yeah, I tested that, so it could be. Store vectors is what we had here in this little portion here. I'm taking like the FC, FD, FE, and FF, the 4 0-page address, and store a copy of them. But I'm not only doing that, I'm also, and I shouldn't clean my source code when I'm talking, but I'm doing that anyway. So FC and FD stored to temp, and then I take FE, I take FF, the absolute value or immediate value FF, and subtract FE and store in temp2. And then I take FF and subtract with the value of 0-page address FF and store in temp3. So when I've done this, temp1 is the actual start address, and temp2 is now the length. Not that weird how much is left. But what I also need to do is I need to take the length and add it to the start address, and then I get the end address. So when this is done, I have temp1 or temp plus temp1 being actual start address, and temp 2 and 3 being the actual end address, rather than this this weird way of counting. I did put also a print routine here that printed the values, but seemingly the raster time I get for doing this is a bit too scarce. So I need to return from the interrupt here before I didn't have enough time to do all the printing. So that's why I'm doing the printing afterwards when I'm doing the saving here, and doing basically as little as possible at this point in time. Okay, more like general utility addresses. This takes counter, the high bind from counter, and prints that, and then takes the low part of counter and prints that. So this prints at in the status box. I feed the address that I want to print in the counter registers, and they are 0-page. I just allocated 2 random 0-page addresses, which you can see in the definitions. And then I feed it with a Y register, because I want to tell where on the command line I would like that address to appear, and that's what this is doing. So I'm just extracting the proper nibble and read from the hex tab using that nibble, and then I poke it to status box comma Y, that's the offset I decided for the number here. Yeah, works fine. Normally I do this for 2 characters, and you don't need the original, so then you just need like that, the counter, and then you would do like that. But feel free to steal that routine. It's I've done it 100 times, and I've tried to optimize it, but it's not really possible to optimize any further. It's just like that. Key weight is the general routine that I had for when I wanted user interaction pressing space. So when it found the original header and you are presented with the name of the file and the start address, I needed a key press there, and I need a bit of a flash there as well, because that is the only place where I'm presenting the start address, and you need to sort of make a note of that, because I don't save the start address in any other way. You need to sort of extract it visually from there. The general print of status addresses, and here again I feed the Y value here to this, and the Y value is the offset that is picked, which means that I can pick different routines here. So the same routine for printing is just fed with different Y values, and then it could pick one of the messages I have here. And as you saw before, file name is also it's stored like here, and this is also the string which is used for presenting the file name. So I'm using the same memory space for both purposes. And this is also then replaced with the start and end address we have calculated here. You will see here in the save address, save function. Save function sets the bank, so I don't need basic, so it should be 36 because I need kernel and I need the IO. Saving message, so it's, you see the logic here, saving message minus messages. That means that the saving message is this one. So whatever address this is on, and then subtracting messages, the sort of the root, that would calculate an offset that goes into the Y. And then when this routine is then called, the Y value would point to this string. Okay, and then I'm picking temp, putting it into counter temp 1 and putting it into counter 1, and then selecting 1D and calling print address. So because this message is now on the screen, this 1D is these 4 initial X's. So it will populate that, and temp contains the start address. And temp2 and temp3 then contain the end address. That was the one we calculated before from this weird way it works. And then that would end up in 23, and 23 is, here, those 4 X's here. Right. Temp counter. Yeah. It looks like this is done twice, but here counter is used as something that I feed to the print routine. But then here the counter is something that is used in the save routine as well, because I'm using the same 0-page address for multiple purposes here. So I'm taking temp again. It looks like I'm doing the same, and yes, I am doing the same here, but it's not for the same purpose. This could possibly be optimized. And then the save routine here is, so it's taking a file, generating a file from this, so the device that we stored from when the program was launched, and it set the logical file. And then it sets the file name, and the file name was this here. So it starts here. The 0 dot is the file name, and then velocipede, the name, would be populated here as it was when we found, and that is extracted from the tape header as we saw before. And then it's sending out the start address and the start address of the file. Counter is then used for picking the values from memory, feeding it out to the output, increasing the counter, and then validating the counter against the end address if we are now on the very end address. If we are not, we're going to make that loop again. So single byte save, proper normal single byte save. And then we close the file because we're done. And then we open the command channel here for seeing if we have any error messages. And if there is an error message, which I haven't validated, but this is Fungus code, basically all of it. So I'm assuming it works. I'm doing key weight that we have an error, and then you're supposed to kind of turn disk and then press space, and then it will try to save again. So you cannot pass this stage unless you have a disk in the drive and where you can actually save the file properly. And then it reads and reads and reads and reads, and yeah, so this is sort of ending the save routine here. 2 general purpose utility routines: tape on, turn tape motor on, and then turn tape motor off. Very logical. That's what they're doing. In the very end, because I'm copying the tape routine, the tape loader onto screen, and in order to ensure that the entire routine is copied, I'm making one of those. I'm filling from the end of the routine to the last address that is copied. As long as that value is positive, then this would fill with a number of spaces. But if it's going to turn negative, which means that the routine is longer than what I'm actually copying, this will give an error. So it's basically there for the single purpose of ensuring that I don't make the silly newbie mistake of writing a routine and then copy just the first half of it, or even missing the last RTS of the last routine could be basically destroying your program. So it's more a way to detect if I've made a simple error of writing a longer routine than my copy routine is actually copying. And then you have the silly header here. That was the 3-line that is on the top of the screen. I've adjusted that since the test you saw before. So it now says that it's microload transfer and it's done for FairLight TV. And now it's version 0.2. It's likely going to be the very last version, so there will never be a 0.1, but it's doing what it's supposed to do. So I say it works. I'm really glad you are still here. Thank you so much for watching this episode. I hope you now have more experience when it comes to how to do tape cracking than you did before. There are aspects of this that you might want to do. I suggest you have a look at this peeling the onion episodes where I'm deconstructing a game and then rebuilding it again. So if you would like to make your own version of Velocipede, yeah, that is this episode, and using the transfer on the game and then taking a look at the peeling the onion is the way to kind of get my insight on how I would approach that. So do that, and I hope you would be good. Thank you so much for watching. Again, it's summertime, so it might be that we won't be available with a new episode next Friday, but hopefully in a Friday very soon. Thank you so much for watching, and all the best. Bye bye.